So today we're going to talk some more about random variables, and the first thing we're going to talk about is something called an expectation. So, for example, what an expectation is, think about the lottery. If you play the lottery like lots and lots and lots of, say, 10 times, how much money could you expect to win in those, out of those like 10 plays? Or you play bingo 10 times, how much would you expect to win in those 10 games? So this expected value is kind of like an average, but it's something called a weighted average. Like your grades in this class, they're weighted averages. Like it isn't as if your homework is worth the same as your tests, right? There's different weights assigned to them because they're sort of a bigger or smaller chunk of the whole, and those weights assigned to them are actually probabilities in some sense, right? It's like 10% homework, 0.1, 50% test, 0.5, right? So, I don't remember exactly what it is, but tests are quite a bit actually. So if you know probabilities for all possible values of a random variable, we can determine the mean outcome over the long run. And this long run average is called the expected value. Okay, so this next blank says the same thing. So the expected value of a random variable x is the mean value of the variable in the sample space of all possible outcomes. And this is the mean value that you would obtain from an infinite number of observations. And for situations that you know a lot about, this should make sense. If you tossed a coin many times, what's the probability that you're going to get your toss equal to a head? 1/2, right? So if you toss it many times, you're going to see that probability gets closer and closer to 1/2. So over the long run. And here's how you find expected value. So the calculation of expected value, or the mean value for a discrete random variable, so discrete means that you can list it as opposed to continuous. And the expected value is the sum. There's a typo right there in your notes. There's like a little lowercase sigma symbol. I meant to make it capital sigma, so just cross that off and make this sigma sign. And then it's x sub I times p sub I. And so what do you think those numbers mean? What is x sub I telling you? Tell you the x value. Does that make sense? What is the p sub I? The probability of that particular value. Okay, does that make sense? You take value times probability over all possibilities. So example 1's a pretty simple scenario, but I can actually give you a table, but we can make a table out of it. So we have this game, and the probability that Mary's going to win the game is 0.01, so kind of low, right? And the probability that she will not win is 0.99. If she wins, she's going to be given $100, and if she loses, she must pay $5. If x is the amount of money she wins or loses, what is the expected value of x? Like how much would she stand to gain or lose if she played this game a long time? So let's make a table out of this. Let's make the x's and the probabilities. So x is the amount of money she wins or loses. So how much money can she win or lose? She can win 100, so that's positive 100. How would you represent losing 5? Negative 5. Does that make sense? What's the probability that she wins the $100? 0.01. And what's the probability that she loses 5? 0.99. So does that part making the table make sense? Okay. There are some games in which you can win like a prize or a lesser prize, right? Like $100 or this, and different probabilities for those. So the expected value of x is equal to a sum of the x's times their probabilities. So the first x is that 100, and what is its probability? 0.01. The next x is times 0.99. So that comes out to be negative 3.95. So first of all, does the whole calculation of x value times probability part make sense? You can do it? Okay, and what the hell does this mean? This means that over the long run, she loses how much per game? $3.95. That isn't actually possible to lose like on one game, right? But it's what would happen if you averaged in her occasional winnings. So is this a game where over the long run, Mary's going to beat the house? No. This is how people have sometimes gamed lottery systems, is they find this expected value. And this was an example of a system. I think it might have been some MIT kids, but I'm not positive. But they found the expected value and figured that it was positive, which means if you played a lot, you would actually come out ahead. Does that make sense? And then they bought shit tons of tickets, and they ended up like making money off of the lottery system because they bought tons and tons and tons of tickets. So this expected value is how you figure that stuff out. If that had come out to be positive, it'd be worth it to play a lot of these games because you would make money. But people who design games also know this, except for in that one case, and they make sure this number is negative. Okay. So the notation E of x represents the mean or expected value of a random variable x. And this little Greek letter that looks like a U, do you know how that's pronounced? Mu. Mu. Like that's the way that I'd spell it. Your book says like mu, like what a cat would say, but that just sounds wrong to me. It's mu is how you spell mu. Like you need a Scrabble word, there's a Scrabble word, okay? So in other words, E of x and mu are the same thing. And your book and I are probably going to use those two things interchangeably. They're just mathematically synonymous, that's all.
So you can write M for mu, or did you just use it?
That's just, mu is just how you spell that.
Oh, okay, I got
Does that make sense?
No, it just, you look like an M there, but it's the mu symbol.
Yep, it's the mu, yep, exactly. Yeah, that little mu symbol is, okay. Okay. And this is just restating the thing that we already said. Like that one example we had where you found expected value or discrete variable only had 2 possibilities, but you can do that if your discrete variable has like 20 or 50 or 70 possibilities. The same kind of principle applies. Number times probability. Okay, so here we have a game, and we are playing the game 3 times. And we assume that they're independent plays, so, the fact that you win one game does not affect the fact that you win the next. And the chance of winning each game is 0.2. So I could have technically kind of made you do this table by yourself, but I gave it to you. But where does this 0.8 come from? God, is that even right?
Should we remake this table?
I don't want to. I'm going to just go with it. But I think it would have come from, so winning all 3 games, how would you calculate that out? 0.2 times 0.2 times 0.2. No, it is, but is the decimal in the right spot though? I think it's 0.008, shouldn't it?
Yeah.
So that's a typo. 0.008. Is that right? That's what it should be, isn't it?
Sure.
Because you do 2 times 2 times 2, the decimal goes over 3 spots. Like, I know it should be 0.008. Because let me just do a quick check. I've got a calculator too. Check and see if they add the 1 now. Because they should add the 1 across the row. I think they do now. 0.512 plus 0.3. Okay. And they now add the 1, so that was a typo that I didn't even catch. So let me make a note of that. All right. How would you find the chances that you don't win at all? What would you multiply there? Like, if your chances of winning is 0.2, what's your chance of not winning? 0.8, right? Because it's the opposite. Either you win or you don't, right? And so this one, 0, you can find by doing 0.8 to the third, right? These middle ones are tricky because you could either win in your first one, your second one, or your third one. And this one you can win the first two, first and last, or second and third. But that's where those come from. Anyhow, it's number of wins out of 3 games. So how would you find the expected value of x? You take the x's times their probabilities. And it's okay if that's 0 sometimes. Like 0 times 0.512 is going to be 0. 1 times 0.384. 2 times 0.096. And 3 times 0.008. Plus 2 times 0.096. 3 times 0.008. I got 0.6 for this. Okay. So write a sentence that interprets the expected value of x in this situation. Okay, so over the long run, that's a good way to start. Because these are really long run averages. So how many times are we playing this game? 3. How many wins do we experience per that 3? 0.6, so less than 1, right? So over the long run, the average number of wins, in 3 games is 0.6. I mean, you're occasionally in your 3 games going to win none, you're occasionally going to win 1, you're going to sometimes win 2, but it's going to be kind of rare to win 3, right? Does that make sense? But if you do lots and lots of trials, on average, you're going to win 0.6 out of 3 times. Which is not an actual possible value to have, but it would be the average. It's kind of like when we had the question about what is average household size. It was like 2.5 people, which is not possible, but it is an average over a large group. Okay. So what did standard deviation describe for these bell-shaped curves we talked about a little bit in the early chapter? 1 deviation is 68, 2 is 95, 3 was almost everybody, right?
Yeah.
So that kind of describes the width of your thing. Does that make sense? Okay, so the standard deviation is roughly the spread. So spread or width, like how spread out your values are. And relative to the mean, which is that middle most common value. Does that make sense? Okay. And similarly here, the standard deviation of a discrete random variable quantifies the same thing, also quantifies the spread. And these are formulas that you just are going to put in a note card. I'm not going to even attempt to tell you like why they are what they are, okay? So just on the note card they go. So when we found standard deviation back in chapter 2, we also found this thing called the variance. Does that ring a little bit of a bell? And what was the relationship between variance and standard deviation?
Variance was the square of standard deviation.
Variance was the square of standard deviation, or to go from variance to standard deviation, you took the square root, right? Okay, now, we used S for estimating standard deviation with a sample, right? The Greek letter that is used for this is sigma. It's a lowercase sigma. Looks like a circle with a tail to the right.
That used to be the S.
That used to be the S, yep. Same as like mean was an M, right? They tend to use the Greek letters that begin with the same letter. Does that make sense? Okay. Now, the way you find the variance is you take your x's minus your mean, right? And then you square them. That's kind of like what we did before, right? And then you multiply by the probabilities. Whereas before we had this whole dividing by n minus 1 weirdness, right? So that's the variance. I do that first, and then to get the standard deviation, you just take the square root of your answer. Does that make sense? Okay. And just like with the expected value, you have to have like one sum for each table entry. This is also like one sum per x, like one term per x. Like the previous one, we had 4 x's, we'd have 4 pieces, right? And to do it, you also have to find the mean, or the e of x thing. Okay, so let's do one. So first find the mean. So mu is equal to e of x. You take value times its probability. So first value is times 0.25. Next value is 0 times 0.5. And then lastly, you have 2 times 0.25, right? Don't freak out when this happens. You get mu equals 0. Okay, is that all right? All right. Calculate the variance. So that's this sigma squared thing. And to do that, you do x value minus the mean squared times the probability. So what's your first x value? And I'm just going to put minus 0 there, so it's obvious that we put minus the mean. Does that make sense? And you square that and multiply by the probability, which is 0.25. What's my next x value?
0 minus 0.
Times 0.5. Plus, and then lastly, 2 minus 0, right? Squared, and 0.25. I think this ends up being 2. Do you agree with me? Because what is negative 2 squared? 4. Times a quarter makes 1. This middle term is 0, right? And this last term is also 1, right? So we have sigma squared is 2. Of course, if you have like on your homework or test, if there's something that's obviously 0, you can like just like leave it out. I just don't want to do it in the notes in case you want to go back and reference it. Okay, how about the standard deviation? Square root of 2. Give me an approximation with 3 decimals.
1.414.
1.414. Okay. This could be a game where you pay out $2, pay out nothing, or get $2 kind of a thing, right? Perhaps. Could be a situation. Negatives usually mean like giving somebody something. Okay. Find the expected value for the number of girls in a family with 3 children, assuming that boys and girls are equally likely. It says to use the probability distribution function given in your text. We actually did this one last time. So what's your guess? Like this is just, let's make a guess. If you have 3 kids, over the long run, how many girls per 3 kids are there going to be? 1.5. Do you guys agree? Like over the long run, on an average, you'll have 1.5 girls out of 3. You can't actually have 1.5 girls, right? But as an average, you can. And we'll figure out why. So if x equals number of girls, and here's the probability that a random variable x equals a specific value. And I think we made this table, like 0 girls had probability 1/8.
Yep.
1 girl had probability 3/8. 2 was 3/8. And 3 had probability 1/8. Having kids, in terms of probability, is just like flipping coins in some sense, isn't it? Just because it's either there's 2 outcomes and they're equally likely, just like having a coin toss is 2 outcomes equally likely. This is the same thing we found when we had like a toss of 3 coins. We tossed a coin 3 times and it was like how many heads, right? Okay. All right, so let's find e of x. So that'd be 0 times n8, right? 1 times 3/8. Oh, I gotta bring up my whiteout marker. Two times 3/8 and 3 times 1/8. So what's that? 3/8 plus 6/8 plus 3/8, which is which is 1.5, isn't it? Okay. And that's what you thought it should be, right? Okay. Now the next question, before we move on to the next topic, is kind of an actuarial question. Do you guys know what actuaries do? They ruin your lives is what they do. So that's kind of a joke. They do things like set insurance premiums and stuff like that so that the insurance company makes money, and that's what this is talking about. So you have an insurance company and they expect that 10% of its policyholders are going to collect claims of $500 this year, and the remaining 90% collect no claims. What is their expected value of payout per person? So let's make a table out of it where X is equal to the payout. And then down here, probability that X, equals some specific value. And of course, payout is not the same for every single person, but they have an average for their 10%. So what is one possible payout? 500. And let's say let's just make it negative because that's them losing money. Does that make sense? Okay, and what's the probability that happens? 0.1. And the other option, somebody said it was 0, and that probability is... Thinking of car insurance, you can go hopefully lots of years and not get in an accident, right? Hopefully. Took me 15 years to get in an accident. Maybe I'm just lucky. And somebody hit me, so it has to remain clear. So expected value of X is going to be negative 500 times 0.1 plus 0 times 0.9, which comes out to be negative 50. Or there's a $50 payout per person in the long run. So that's how much they expect to pay the people if they get in over the long run per person. So how much should your insurance cost if the company wants to make money? More than that. So if they say they want to make $20 per person, then the price should be set at 70. If they want to make $50 per person, they should set it at 100. Does that make sense? Okay.
And this is per year or per month?
That's not clear. I would expect.
They expect to collect claims of 500 this year.
So it probably would be a price per year, but it's really cheap. So who knows? I mean, it might make more sense for it to be per month. I don't know. Per month seems like a more logical interpretation based on what insurance actually costs people. Right? Does that make sense? And it depends also, it's different for different insurance premiums too, right? You have the liability one that's super cheap, and then you have the one that includes coverage, like the collision coverage, so anyway. Okay, so that stuff's not so bad, right? Okay. The next stuff is a little bit harder. I don't want it to freak you out, it just actually is a bit trickier. So there is a specific kind of discrete random variable, it's a bit special and it comes up a lot. It's called a binomial random variable. And certain conditions must be met for a variable to be considered binomial. But the basic idea is that this is a count of how many times a variable occurs or does not occur. And you see in the word binomial, you see this prefix by meaning two. So what this means is you have lots of trials and there are two possible outcomes, like win-lose, boy-girl, heads, tails. Does that idea make sense? You are this thing or you're not that thing. There are two things. So some examples would be tossing a coin, where the outcomes are heads and tails. So the idea is you toss a coin, say 10 times. How many heads are going to come up? How many tails are going to come up? Or having kids, we'll say. And we're going to not go into gender identity. Not that I don't care. It's just that all of a sudden it's no longer binomial. So boys and girls. Or something where you win, you lose. Okay. And with a binomial random variable, you assume, here's what you assume. You assume you do some, we'll call it a trial, a fixed number of times. We call that n. For example, you toss a coin 10 times. You do the experiment of tossing coin 10 times. That's your n. Then the variable x stands for the number of times an event occurs in n trials. And here's a really quick example. Toss a coin 3 times, x equals number of heads. We did this one, didn't we? Okay. What were the possible values for x? You could have how many different values for number of heads? Starting from the lowest. 0. You could have 1. You could have 2, or you could have 3, right? If you tossed that coin 10 times, what would that list be? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Does that make sense? Or we had the thing with somebody had 4 kids, right? X is the number of girls. The possibilities would be 0, 1, 2, 3, or 4. Yes?
So wouldn't it be easier for a binomial variable just to say that x is always going to be equal to 1 plus the amount of time?
Well, x can be any of those values, but it will always be 0 up to the n. Does that make sense?
Right, that's what I'm
There'll
saying.
always be one more thing in that list than there are number of tosses. Yeah, that's what you're trying to say. Okay. So here are the conditions for this experiment. There are n trials, and this number n is specified in advance, and it's not random variable, which means it's not changing. Does that make sense? So n does not change. It's fixed. The other thing is that there are 2 possible outcomes, and the outcomes can be called success and failure. Like success could be toss head, then failure is that you toss a tail. Does that idea make sense? Success could be having a girl because girls are awesome. Just kidding. And, well, not the girls are awesome, but boys are not all, okay. And then a boy isn't a failure. Just, okay, that wasn't clear. The other, I know, so eloquent. The other thing is that outcomes have to be independent. That's one assumption you just kind of usually make, that tossing a coin is independent from one toss to the next, having your second kid is independent of the first. And then the probability of success remains the same from one trial to the next. So we use the letter P to talk about what the probability of success is. And because there are only 2 possibilities, what's the chances for failing? 1 minus P, right? Because you either fail or you succeed. If we're talking about a coin toss, what would P be? Like, so P would be 0.5, right? And then 1 minus P would also be 0.5. If we're talking about having kids, they'd both be 0.5 as well, right? But suppose I tossed a die, which I know has 6 things, but I said success is you get a 1, fail is anything else. So success would be probability 1/6, fail would be probability 5/6, right? Does that make sense? So, yes.
So is it like the complement kind of thing?
Yeah, exactly. This is the complement thing. Yep.
Okay.
Success has a probability, and then the failure is the complement of success. And then the question is if I do this experiment 10 times, for example, how many successes am I going to have? That kind of a thing. What's the chances of 1 success, or 2 success, or 3 success? Kind of like with that question we had about the heads and tails. What were the chances of there being like 0 heads, 1 head, 2 heads, or 3 heads, right? And they were all different. Well, kind of. So here is the formula that finds that for more complicated situations. I know, yeah, it's gonna be what? Okay, so we're gonna use it, but it's a note card thing for now. But let's talk about what those numbers mean. And I have an example, like example 6. I can show you why this matches something that we already did. Okay. So first of all, have you guys seen that little exclamation mark symbol before? If you haven't, that's okay. But here's what it means. If I give you 5 followed by an exclamation mark, what that means is 5 times 4 times 3 times 2 times 1. You start with that number and multiply every integer from that down to 1, or from 1 up to that number. Does that make sense? That's what that means. It's called a factorial. It's a very, very happy number. Okay, so let's talk about what this thing means a little bit. So n is the number of trials you do. Does that make sense? So in this formula, you see how the n shows up here, there, and there, right? K is like saying, if I toss a coin like 10 times, what's the chances I'm going to get exactly 5 heads? There's a specific value. What's the chances x equals 5 heads, or 4, or 3, okay? And so that specific value is your K value. And then this probability tells you success to that K power, and this is failure to the n minus K power. So let me show you a specific one with the whole having kids scenario, and I can make you believe that they do the same thing, okay? What this does is it sort of that factorial business out in front counts the number of ways you can arrange like the successes and failures within a list of, say, 10. Kind of like when we had heads, if you had exactly 1 head, you could have had it first, second, or third, right? There are 3 different ways to do that. That thing in front is doing that counting. And I can at least make you believe it's the same thing with this next example. Okay, so let's do this one, kind of pretending we don't know the other way, and then we'll try the other way and tell you how it works. So suppose you have 5 kids. What's the chances that exactly 1 is a boy? So first of all, how many trials do you have of an experiment? 5, so n is equal to 5. What's the probability of success? 0.5. Okay. Now let's just pretend that formula makes no sense to us, which I do agree that it probably, at this stage probably does. So let's just list the ways that you can have 5 kids where 1's a boy. You could have had a boy first, right? So boy, girl, 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 girl. Does that make sense? And that's going to have probability equal to, what's the chances of having that first boy? No, what's the chance of having a boy on birth 1? 0.5. And then this, the girl, 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 that's all the failures, right? Not saying girls are failures, just really not. That's 0.5 to the 4th, right? I know that becomes 0.5 to the 5th eventually, but I want to keep the success different from the failure kind of thing, if that makes any sense. Is that the only way to have 1 boy out of 5 kids? What else could have happened?
Girl, boy, girl, boy.
Girl, boy, girl, girl, girl. Is the probability going to change? No. How many? There's, I think, 3 more ways, right? Girl, girl, boy, girl, girl. Will that probability change? Nope. Could have been girl, 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 boy, girl. Same probability. And what's the final option?
Boy last.
Boy last. Yeah, boy last. And so the probability of having one boy means you just add all these up, right? Does that make sense? Because either you have a boy first, second, third, fourth, or fifth, right? They're mutually exclusive events. You can add the probabilities. So probability of, we'll say x equals 1 is 5 times 0.5 to the fifth, which comes out to be 0.15625. Now, can everybody agree that listing all the possibilities is a big pain in the behind?
Yes.
And it's probably, and I think, like, what if you had 2 boys and 3 girls? You'd have to do, like, boy, boy, girl, 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 and it's going to be, like, lots more cases. Does that make sense? And all of a sudden, what if you talk about 10 kids? It's like a zillion more cases, right? So that's where that formula that I gave you comes in pretty handy, because it does this kind of thing. That's what it's doing. So you guys have it written on your paper. I'll just write it down. Px equals k is n factorial over k factorial, n minus k factorial, p to the k, 1 minus p to the n minus k. The hardest thing is figuring out what to put into these places. Once you get that, it's not that bad. So first of all, what's the specific value that you care about for k?
Boy?
Boy, care about one, and the kicker is one boy. Does that make sense? So k, one success.
If it was 2 boys, would we say k to the second?
You wouldn't say second power, you just say k equals 2. Does that make sense? If it was 2 boys, you'd plug in 2 for k. 3 boys, plug in 3 for k. 4 boys plug in 4 for k. 5 plug in 5. 0 plug in 0. Oh, one special thing. 0 factorial is defined to be 1, okay? It's weird, it's strange, just accept it and move on. Okay, good, done. Okay, so we have n is 5, p is 0.5, k is equal to 1, because we're told we want 1 to be a boy. So then just plug the numbers in. So what goes in for n? 5, so we got 5 factorial over what goes in for k? 1. And then n minus k, is 5 minus 1 makes 4. What's our probability of success? 0.5. To the k power is 1. Notice that's our, like, one success of having a boy, right? And then what's the 1 minus p equal to? Also 0.5, right? And those are all of our failures. How many failures are there? 4. So does that look a little bit like what we had before? And then the question is how the heck does this thing simplify? Well, think 5 factorial is 5, 4, 3, 2, 1, right? 4 factorial is 4, 3, 2, 1, right? So what does 5 factorial divided by 4 factorial give you? 5. So that's the 5, 4, 3, 2, 1 over 1, 4, 3, 2, 1. All of those things cancel, right? Does that make sense? That's a 4, yeah.
That is a y. I was like, wait a second, she's at variables.
No variables. But do you see how these came out to be the same thing? And what this formula saves you the trouble of doing is having to list all the possible ways that this thing could happen, which is particularly helpful when you have, like, large n's, right? Should we do another one? Yes.
I'm confused.
Which part?
What's that? Oh.
Oh, that's 0 factorial. So just like this 5 factorial means 5 times 4 times 3 times 2 times 1. Just because you have to use it, 0 factorial is defined to be 1. That's just something that people
So it
will
won't
say.
be 0.
It won't be 0. 0 factorial is equal to 1.
So that's not the answer?
No. This is just the thing this is the answer. This is, you might have to use it eventually. It's just a special thing about factorials. I should have put it elsewhere. Probably on the first page. Or like up in the above part. Yes?
So I get the 5 factorial on top. Why is it 1 times 4 times 3 times 2?
Because 1 factorial is just 1. I mean, right? Because it's number down to 1, well, if the number is 1, it's already down at 1. So, but does that 1 affect anything? No, so it doesn't really matter. Okay. So let's try the next one. So for each of the following random variables, specify n and p. And remember that n is the number of trials. Think number of times you play the game. And p is the probability of success. There's no reason you have to say it's success, but just to be consistent, let's do that. So a company puts a game card in each box of cereal, and 1 over 100 of them are winners. You buy 10 boxes of cereals, and X is the number of times you win. So what is your N? You play the cereal game 10 times, right? What's your chances of success? 1 out of 100 or 0.01? Does that idea make sense? Okay. Jack likes to play computer solitaire and he wins about 30% of the time. We'll let X equal the number of games he wins out of his next 20 games. So how many trials? 20. What's his chances of success? 0.3. Okay, let's do something else with this. I'm just going to add a little question in here. Let's say, what is the probability he wins exactly, we'll say 12 games. So what is that number 12 telling me? Which part in that binomial formula thing? This, the k equals 12, right? Yep, so k is equal to 12. Very good. So we're going to find the probability that x equals 12. I'm just going to write the formula down. It's n factorial over k factorial, n minus k factorial, p to the k, 1 minus p to the n minus k. You don't have to memorize it, you just know how to use it.
So most likely you'll put the equation on a quiz if we need it? or-
You'll put it on your note card.
Oh, I just wanted to clarify that.
Yes, yes. You need to put it on your note card. Yep. Because otherwise I want to give you too much of a hint as to what you should use. Does that make sense? I want you to know this is what you're supposed to use. Hence the note card. I know, it's evil. So what goes in for n? 20. What goes in for k? 12. And then n minus k is 20 minus 12 or 8. Great. The chances of success is 0.3. And the chances of failure are then, so 0.7, right? And then to the power of, do you see any pattern with these exponents? What do they have to add up to? 12 and 8 have to add to 20? You have to add to n because you have so many failures or successes and so many failures out of that total number of trials, right? And from here, you just know how to put this in your calculator. So calculators usually have factorial buttons. If you have one like me, it's under the PRB thing. PRB stands for probability. So you have to find that on your calculator yourself. Because they're all going to be a teensy bit different. If all else fails, you could make them multiplications. Does that make sense? Like 20 factorial is 20 down to 1, right? 12 factorial begins at 12 and goes down to 1, right? So if I cancel some stuff out, couldn't I just go 20 down to 13? Does that make sense? So I could go 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 divided by...
And why are you only going down to 13?
Because 12 factorial goes from 12 on down? Does that make sense? So you're going to cancel all the remaining stuff with this guy, right? And then 8 would go 8, 7, 6, 5, 4, 3, 2, 1. And then you can just punch the rest in the calculator, blah. Okay, you do that, you should get 0.00386. One place you can mess up when putting this in a calculator is that if you want to put that whole denominator actually in the denominator, you have to have parentheses right there. Okay, so before you do your division, parenthesize. Okay, otherwise it only is going to put the first one in the bottom, not the second one as well. Do you see what I'm saying? So put parentheses, like in your notes there, so you know to put them in your calculator there. I'll also tell you how to use Excel to calculate these. You can check your answers, but on your test you can't use Excel. You have to know how to punch the buttons in your calculator correctly.
So it's called NPR?
Nope, there's a little button that's actually an exclamation mark eventually if you scroll over. You see it?
Yeah.
Okay.
If you scroll over with what?
If you scroll over, there's a little, everybody's is different, so let me answer individual calculator questions like after class because they're all going to be a little bit different. Okay? No problem. Okay. So here's another one. And I know this is hard, so like in tomorrow's lesson, at the end of it, I've got a review of this. You got a question?
Could you just go back to answer real quick?
Yes. So suppose that in a very, very large population, 10% of individuals are left-handed. We're going to sample 5 individuals, and the random variable x is the number of left-handies you have among those 5 people. Find the probabilities of the following events. We'll do these by hand, but I'll also tell you how you can use software to check your answer, okay? So first of all, what's our n? 5. What's our probability of success? 0.1. So success is having a lefty. You could also define success as having a righty. It's going to work out the same. It's just all the questions are about left-handed peoples. Woohoo! Who's lefty? Yay! I'm not, but I wish I was because that'd be cool. So.
They don't live as in.
Okay, what's the chances that exactly one person is left-handed in the sample of 5? So what's our k in that case? K is 1. Yep, no trick there. K is 1.
So do 0.5.
No, because,
Never mind.
yep, it's kind of like the whole having exactly one boy out of 5 kids, right? Except for we have left-handed people and they're not equally likely. So that formula was n factorial over k factorial n minus k factorial p to the k 1 minus p to the n minus k. And that was for x equals k, actually. Okay, so what goes in for n? 5. What goes in for k?
1.
So 5 factorial over 1 factorial, 4 factorial. Success was 0.1 to the 1. And then what's your non-success probability? 0.9 to the 4th, exactly. And that's pretty similar to the boys and girls one, except for the fact they've got 0.1 and 0.9, right? What's that 5 factorial over 1 over 4 factorial going to cancel out to? 5. So that's 5 times 0.1 times 0.9 to the 4th. And you don't even need to know how to use factorial buttons to do that in a calculator, right? I'll try to keep them on tests and quizzes a little bit nicer, but I can make no promises on your homework. Does that make sense? As in the factorial button thing. 0.32805 is what I got. Does that part make sense? Sure?
Yep.
Okay. At least how to plug stuff into the formula, right? Okay.
Are you gonna want it to 5 decimal places?
Probably not.
So like
So-
round it to 1.
So let's just say 3, just to be, so that'd be fine with me. So 0.328 is good enough. At most, one of the 5, so, oh gosh, okay, vocabulary.
So what's that?
So at most 1 means 1 is the biggest, right? So that means 1 or 0. So it's probability that x is less than or equal to 1. That's the probability that x is 0 or x is equal to 1. Does that translation into that make sense? So So if at most 1, that means 1 or none. If I said at least 1, that would mean 1 or more. Does that make sense?
So
Okay.
then with at least one, will we have to plug in like?
A gazillion of them? Yes. I'll show you how to do this faster as well, okay? So this one we already did. Does that make sense? We just need to work out what this guy is.
Wait, I don't know if I wrote it down wrong, the first one, but I had K equals 1.
We did, yep.
Okay, so that's the same thing?
Yes, exactly. Okay, so let's find this guy. Probability that x equals 0. So that's still 5 factorial over, what's instead of 1 factorial, it's now? And then 5 factorial again, right? And then we have success, which is 0.1 to the power of 0, and 0.9 to the power of 5. And this is where that whole 0 factorial equals 1 thing comes up. Do you see what I'm saying? Like, otherwise you have a division by 0, and division by 0 is not okay, right? So 0 factorial is just defined to be 1. So 5 factorial of 5 factorial just makes 1. That's 0.9 to the 5th, right? And you can think, okay, that'd have to be righty, 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 which is what that 0.9 to the 5th is doing, right? So that comes out to be 0.59049. I just kept all the digits because I was feeling like it. And so then in that case, what is this probability that x is less than or equal to 1 from above? Like what's this?
Add those?
Add those, yep. The 0.59049 plus the other one, which was 0.5, and they came out to be, there we go. And that should kind of make sense, right? If only 10% of people are left-handed, it's pretty likely you're going to get samples that have no lefties in them, right? Yes? Is that it? Yep, I can scroll it up. So see if you can do C using the answers to B.
Oh, my goodness.
Is everyone okay with, did you get B written down or not quite yet?
No.
Any questions about B?
Yeah, I'm just confusing that last step, right? Where the 0, no, right above that.
Yeah.
Yeah, so what happened there,
Oh, well, this first thing becomes 1.
right?
Anything to the 0 power is also
0.
1. Oh, yeah, stuff to 0 power is 1. Yeah. I thought I should have reviewed that, sorry.
No, you're good.
Yep. I can actually give you a really good mathematical reason, but I don't think I have time today. Okay? Your calculator will verify it for you, though. Stuff to 0 is 1. Okay. This next one, what's the chances that 2 or more individuals are left-handed? So that's technically px bigger than or equal to 2, right? Which would technically be probability x is equal to 2, x is equal to 3, x is equal to 4, and you want to hate me right about now, and also x is equal to 5. You're like, grrr, hate my book. Except, you notice, this is the opposite of what we did in part B, isn't it? Yeah, so watch out for stuff like that on the homework, okay?
I would realize after I did it.
1 minus answer to B. If I say that, is that clear enough? Okay, so watch out for complementy type things, because the other way will work, it's just going to be extremely painful. So 1 minus 0.91854 works out to be 0.08146. Okay. So the next one, I'll show you how to do this using Excel. Like I'll just tell you what the Excel commands are. So suppose you have a 15-question true-false quiz and you haven't studied. This happens in life a lot, right? And you want to guess on every single question. You're like, oh, true-false, yay! What's the chances that you're going to pass with at least 10 correct answers by guessing alone? So you want the probability that x is bigger than or equal to 10. Does Does that, where X is like the number of things you get correct? Does that make sense? Oh, how many trials are here? What's your, 15? What's your probability of success?
0.5.
Because it's a multiple choice, so true, or true, false. Okay. So probability X is bigger than or equal to 10. So now Excel only goes, inequalities go the other direction. They always go less than or equal to. So you've got to change this into a complementary type thing. So having 10, 11, 12, 13, 14, or 15 is the same as not having up to 9. So this is equal to 1 minus probability X is less than or equal to 9. And so that's like having 9 right, 8 right, 7 right, 6 right, 5. You don't want to do that by hand. That's going to be a pain in the butt, right? In Excel, here's what you do. You put in a little equal sign, type in this variable called binom dist. What do you think that stands for? Binomial distribution, right? So first you put in your K, then you put in your N, then you put in your P, and then you put in something that's either put in true or you put in false. And I think you all know, for this particular one, what are we going to put in for K? If we're looking at this guy, what do you think the K is going to be? 9. What's the N going to be?
15.
What's your P going to be?
5.
Okay, and the other question is what the heck's up with this whole true-false business, right? So true, let me make sure I get it right. True does the less than or equal to business. False just does 9 exactly.
So you need true.
So you need true.
Wait, could you say that again?
True does less than or equal to, because it's answering a question. What it's answering a question is, the question is answering is this a cumulative distribution function? Which means, is it all the probabilities up to this value, yes or no? And this is saying yes, otherwise it's saying no. And that's just a design choice in Excel.
So false only does K.
False only does K equals 9 exactly, whereas this one does everything from 9 on down. Okay?
So whatever you put in for K, that's how you just do.
Yep. What this comes out to be is 0.1509.
So low probability.